All right. Hey, AP Physics students, this is Barry. I'm here to talk to you today about Unit 1 Kinematics. I'm going to read through the notes that will also be posted on the website. So let's get right to it. This is our first big unit, and we're going to talk about what kinematics is and how we're going to learn all this fun stuff. First thing I want to do is talk about how we're going to handle a lot of the prep for AP exams as a whole. The AP Physics curriculum per College Board is broken down into 6 big ideas. These encompass core scientific principles, theories, and processes of the discipline. They run through all of the concepts involved in physics as a whole, and they're key to the understanding of how interconnectedness of physics. And so they're going to be prevalent in a lot of our units, and I want to make sure to highlight which ones we have as we get into each different unit. So they'll be laid out to start each unit to make sure to help with your understanding. And this is a little odd, but we're not going to start with big idea 1. The 2 big ideas that are included here in kinematics are big idea 3 and 4. So I want to go through what those are, and then we will develop further understanding and get to the other big ideas as our units approach those, okay? So big idea 3, the interactions of an object with another object can be described by forces. And forces are going to be the highlight of our second unit, dynamics, but forces are going to drive motion, and so thus are very important for kinematics, which is our unit on motion. And big idea 4, interactions between systems can result in changes in those systems. So as something happens, we're going to have a change in a system as far as potentially a change of a location of an object, the velocity and speed of that object. That's going to change is going to be known as acceleration. These terms are really what we're looking at here for this unit. So keep them in mind, please, and think about where you might see them throughout, and we will revisit them at the end of these notes as well. I want to start first with the language of physics. First thing, mechanics. This is the study of the motion of objects. This is really what Isaac Newton focused on when he first talked about classical physics. He studied the motion of objects and defined a lot of things within that. And then more specifically, where we are right now is kinematics. This is the science of describing the motion of objects using words, diagrams, numbers, graphs, equations, all these different things to describe motion of objects. And you see the motion of 2 different people down here at the bottom. And we could describe the changes in that motion as they move through whatever movements they've got going on here using these different terms that we're going to talk about. The first thing we need to describe is distance versus displacement. And these terms are very similar and probably things that you've used similarly up to this point. Distance is a numerical description of how far apart objects are or the length of a path that a moving object follows. And displacement is the shortest possible path between 2 points. This is going to move back to something we covered in our intro unit, scalars and vectors, as well as we talked about some differences between these here. But really, distance, think about that as along a path, we have a step-by-step vector connection, whereas displacement would just be one vector from where you started to where you finished. Position is going to be marked by the variable x in this class. Distance will have a total length traveled, that's typically d, and displacement would be that change in position, delta x or delta d. Both are going to be measured in meters, and you're more commonly than anything going to see x represent a location of an object, and thus a distance covered will be that delta means change in, x or potentially delta d as far as the distance being traveled there. A quick brainstorming activity. And we're going to cover this as an intro to one of our units here coming up as we actually do some in-class activities. So I'm going to skip these now as I read the notes, but we will go through these brainstorming activities as a group. But I want to show this image right here to show that difference between distance and displacement. I think it's really helpful to see what's going on. So if we start up in the top left corner of this here, well, I guess the far left side, where the purple and the green dotted lines begin, that's going to be our starting location. A person is walking the solid line path, as you see in the bottom right there, the path taken to get to that final spot. The distance that they cover would move along that path, whereas the displacement would be the change from where they first started to where they finish. All right, along those lines, we need to get into speed versus velocity. These are used a little more interchangeably. Distance and displacement are pretty unique and do stand apart often, but speed and velocity oftentimes will be used together as the same term essentially, but I do want to make sure that we understand the difference between them. The distance traveled by an object over a specific time interval is the speed, and then the velocity is going to be the rate of change of a specific object in a given direction as it travels from point A to point B. You'll notice There's one extra blurb in that velocity definition, and it is that it is given in a given direction. That moves back to what I just mentioned before, scalar versus vector. One of these is a scalar, one a vector. And a great way to think about this, a speed limit sign that you might see somewhere is literally telling you the speed. It's telling you the right thing. It is not a velocity limit. It is telling you a speed limit because it's saying the maximum speed in this area, let's say, is 35 miles per hour. That's just giving you the value. It's not telling you what direction you are and aren't allowed to go. It's just telling you that the maximum allowed is 35 miles per hour, just a magnitude, so it's a scalar. Whereas a velocity might be kind of the combination of information that you get from your GPS. A lot of GPS technologies show you what the stated speed limit is where you're moving, but then we'll also show you the directions you need to move in order to navigate from A to B. So it's showing you both direction and magnitude, so it's technically giving you a velocity. The time as we measure things here in physics is going to be measured in seconds, and so our standard unit for speed and velocity is meters per second, not miles per hour. And we'll talk more about that as we get to some specific problems. We've got another brainstorming activity, and again, we'll visit these when we actually have class in person as opposed to this recording. As you're calculating velocity, I want you to think about a few things here. What would you need to calculate how quickly an object is going? And we'll do this activity as well, but what would you need to do that? And so we've got our speed here. It's going to be distance over time, velocity displacement over time, and then we've got displacement as our change in position and distance traveled from initial to final position. So I just wanted to kind of build up here to our final that delta x is important. All right, the change in x, the change in position. Without that change in position, we're going to have a speed and a velocity of 0, right? There's no movement, then there's no speed and there's no velocity. So that delta x is important. Now the nomenclature that you see there is important as well. That f, as far as the bottom of the first x, it is denoting the final position, whereas the I after that second x is the initial. So you'll see that a lot, I and f, initial and final. Sometimes you will see a little 0 instead of the I, and that's referred to then as x naught. And what that is telling you is it wants the position when the time equals 0. So x with the subscript 0 there is referring to x at the time of 0. All right, so we've got a little bit of practice here. And again, we'll get into these types of questions as we get into a group situation. I do want to talk about acceleration, though. So we've talked about distance and displacement, so our position there, velocity and speed, and so our position per an amount of time. Now, there's potentially a change in velocity as well, and acceleration is what's going to define that change in velocity, as you see there on the first line. Now, you've heard me already say in our intro unit that positive and negative are just direction, and that's something to note here very specifically, because when you think of a positive velocity or a negative velocity, you think of moving in the forward direction or moving in the backwards direction. But we can have a positive and a negative acceleration as well. A positive acceleration would be increasing a velocity. A negative acceleration would be decreasing your velocity. You might hear things like decelerate, but I want to make sure we get the vocabulary right here. So here in physics, we're going to have positive acceleration, negative acceleration. There are a lot of misnomers about acceleration, so I want to hit that real quick. So sports announcers often will say, sports or other general public will say that that a player is accelerating as they are moving fast, right? So we've got, of course, our NC State football here. I mean, this guy's about to score a touchdown, duh, it's the Wolfpack. But I want to highlight how it's not true that they accelerate when they're moving quickly, okay? The handoff is happening right here. You see that play happening, and the linemen are moving to the right. The running back's going to move off to the right. It's pretty obvious that that's all going to happen, okay? This player better not be accelerating once they get outside and start moving down the sideline. Because if they don't accelerate right now, they're not going to get around the edge there of those defenders and be able to be moving at their highest velocity. They need to accelerate right now and be at that highest velocity as soon as possible, okay? So it's more about where it's happening than the difference between velocity and acceleration, but I want to try to hit a couple of those misnomers as we move through some of this material as well. Acceleration. Well, quick review there to start us off. Velocity is that change in distance, or delta x, and I'm kind of purposely putting both in here a little bit, and I realize that that's, again, speed and velocity a lot of times interchanged. It's going to be the change in that position over the change in time. So acceleration is how quickly an object's velocity changes. Acceleration can be speeding up, V and A are in the same direction, slowing down, there's a different sign for V and A, and changing direction So we could be moving around in a different direction and thus have an acceleration because of that. Now that's something that we'll get to in a different unit, okay? But that'll come up more later as well. When we calculate acceleration, we need to have a change in velocity over a change in time. So that final versus initial minus initial again over time. And if we looked at a quick example right here, I do want to mention this one real quick because I think it's very important. I want to know what the acceleration of a car is if it goes from 0 to 60 miles per hour in 3.5 seconds. And these are both things that are commonly referred to, right? Big acceleration, right? You hear about a muscle car maybe. It's going from 0 to 60 and whatever. I want to talk about that because we've got a common misnomer here as well. Right? So what we're looking at if we plug our numbers into that equation is 60 miles an hour minus 0 miles an hour divided by 3.5 seconds. So I now have 17.1 miles per hour per second. What's wrong with that? And we'll expand much more about this soon, but the units for that are a train wreck. You can't have hours and seconds in the same unit there. This makes no sense. Okay, so the units for acceleration are important also. Acceleration is calculated by dividing velocity in meters per second by time, seconds. So the units become meters per second, again, divided by seconds per second. So meters per second, or commonly written meters per second squared. Okay, those two terms mean the same thing. So meters per second and meters per second squared are the same thing. Please note that. You'll probably see the second one more commonly than the first. Make sure the unit of time and velocity is the same as the unit of time used for the time elapsed. That's very important. If you were to see a problem that talks about a change in miles per hour and it gives you the amount of seconds, you're going to have to change your values there to properly fit the units. And we've done a little bit of review from chemistry and talking about how quantities can change that, so just keep that stuff in mind. Your units have to match. All right, we need to get into how graphs of motion can describe motion of an object. There are going to be 3 types of graphs that we're going to talk about. We're going to get a lot of practice with this, but I want to highlight the basics of them before we get to that point. First, whenever you have a graph, your independent variable will go on the x-axis, okay? And it is the variable that cannot be altered. We're going to have all 3 of these types of graphs be verse time graphs. Time per second cannot be changed. A second is a second is a second. And you'll hear me say that a lot as we go through this stuff, okay? But please realize that. So time will always be what's on the x-axis. If you make one of these graphs, it needs to go on the x-axis. That will always be the case. The big question here is going to be what's on the y-axis. All right, so first thing you should do whenever you see a graph of motion, look at the y-axis, see what's there. And right now I see that this one has position in meters. Right, so if I have position on the y-axis, that's telling me that location that something's at, right, that x value. Okay. From there, we just need to understand what a graph is and how it works in order to make all of this work for us. So if we look, and I'm not even going to look at what I've written there yet, I want to just walk through this real quick and see what's happening. So from 0 to 1 seconds, this person's or this object's position does not change. So there is no motion and thus a velocity of 0. Okay. From 1 to 3 seconds, there is movement from 20 to 60 meters. So we have some sort of velocity in between that time. From 3 to roughly 4.5 seconds, you see there, again, staying at that location of 60 meters, so there would be a velocity of 0 again. And from 4.5 to 6 seconds, we are going from 60 meters back to 20 meters. And so we would have a velocity there as well. So I want to look at a few things here on the left when we go back to these questions real quick. The positive slope means that we would have a positive velocity. Okay, so from 1 to 3 seconds, we have a positive velocity. The negative slope from 4.5 to 6 seconds means we would have a negative velocity. In both cases, we have a velocity. It's just about the direction we're moving. So we moved from 1 to 3 seconds forward from 20 to 60. From 4.5 to 6 seconds, we moved backwards from 60 to 20. All right. No slope is the last thing to look at, and no slope on a graph like this implies no movement whatsoever because the position remains the same. Now, an important note here, in the 2 sections of motion, I could potentially ask you on a test, on a quiz, on something, which one of these has the greatest velocity? I wouldn't be looking for which one is positive and which one is negative. I would look for the greatest magnitude. That would happen at the negative velocity on the right of the graph because that same change of 20 meters is happening over less time. So if I look from 1 to 3 seconds, I have 40 meters of delta x of change in position over 2 seconds. So I'm moving at 20 meters per second. Okay. On the other end here, though, we have 20 meters. I'm sorry, that was a miscalculation. Apologies. We're moving no, it's not 40 meters over 2 seconds. And so you are moving at 20 meters per second. On the back end, I'm sorry, y'all. On the back end, you're moving from 4.5 to 6 seconds, and you're still moving the 40 meters. So you'd have that 40 meters divided by 1.5 seconds, and that would give you over 20 meters per second. We'll just say that since I don't have a calculator right next to me. Sorry. And you'd be moving in the negative direction, but still at a greater magnitude overall. Moving on to the next type of graph. And again, we want to look at that y-axis right away to know what type of graph we're looking at. You've got the time on the bottom there, and we have velocity on the left side. So if I flip back real quick, again, here, I had a spot where there was no slope, I had no velocity. So that must be the same case here, right? So if I look from 1 to 2 seconds, I must have no velocity because there's no slope. Same thing from 4 to 7, right? No, that's not the case here. All right, we need to look at what the graph is telling us. So since we have velocity on the y-axis here and time on the x-axis, I need to find, if I were to try to look for the spots where this object is not moving, I want to see just where velocity equals 0. And that's at 0 seconds and then up at 9 seconds. Those are the only locations here where this object is not moving. From 0 to 1 seconds, we are increasing our velocity, thus accelerating from 0 to 1 meter per second. And from 1 to 2 seconds, then, we are holding that velocity the same. Okay? 2 to 4 seconds, increasing velocity from 1 to 3 meters per second. 4 to 7 seconds, no change in velocity. And then 7 to 9 seconds, we have a change in our velocity as well, but in the negative direction because we have that negative slope. Okay, so I want to look at the questions again on the right, and they're the same questions that we asked before. What does a positive slope mean? Positive slope here would mean positive acceleration because we are increasing our velocity. So from 0 to 1 and from 2 to 4 seconds, we have a positive slope and thus a positive acceleration, speeding up. Okay, from 7 to 9 seconds, we would have a negative slope, as you see the second question asked for, and thus a slowing down, a negative acceleration. No slope here is actually going to mean no change in velocity and thus a constant velocity. Okay? Now, it's important to be able to read these graphs. There's 6 questions asked right there that are potentially questions that could show up on an AP test. Okay? You shouldn't try to memorize the answers for those based on the type of graph that it is. If you can just look at the graph and read the graph, then you could answer and interpret those questions on your own. That's what I wanted to look at here, okay? The last type of graph, and by far the least common graph, and one that I wouldn't necessarily expect you to see anywhere, but that we want to talk about anyway, is an acceleration versus time graph. And every so often you do see all 3 different types put together. We need to look once again at the y-axis. And we see that A there, and we see meters per second squared, so we know we have an acceleration. And then on the x-axis, we have our time. And this looks a bit different because you have that drop, that big step, okay? We're going to see straight lines like that because this is an algebra-based class. In a calculus-based class, you would see more of a curve there. But what we've got is an object that is accelerating during the time of 0 to 3 seconds, positively accelerating, so speeding up, increasing its velocity. And from 3 to 5 seconds, it is negatively accelerating, so it is slowing down, decreasing its velocity. I want you to think for just a second, or maybe pause this and look at this graph, and tell me on here, do you see a spot on this graph where the velocity equals 0? We looked at that for the previous ones, so pause real quick, find on here where the velocity equals 0. Now that you're back, I've got to say, trick question. You can't tell that. We could have a number of different things explained by this graph. Okay, you could have an object that is stationary, and then it starts moving, so it accelerates positively. Okay, and then after so much time, it stops moving where that line drops at t equals 3 seconds. It starts moving backwards. So it just changes direction quickly and then starts increasing velocity in the negative direction then, okay? You could also have an object moving it along the highway that decides to accelerate to pass a car. So we've got that positive acceleration there, and then slows back down just to make sure they're not getting a ticket while they're driving on the highway. Both of those things could be the case. You cannot be sure at any point on this graph that we have a velocity equal to 0. So that's important to note. So a positive slope here, a negative slope, no slope, all those things on an acceleration versus time graph are going to be much less important. But I wanted to ask those same questions, okay? So we're not really going to have sloped lines here. We're going to have either flat lines that tell us a value or a step. And I wanted to make sure to point out the difference here in these types of graphs. All right, as you have objects accelerate, we could explain the motion of the car that you see at the top here with all three graphs. And it does show these as integrals. That's what that squiggly S means. And that's a calculus function and not something you need to worry about for this right now. But it shows, for those of you maybe who have had calculus, the correlation between these different things, okay? So the vector arrows up at the top for this car are meant to signify a positive change in velocity of the car. And we see that in the middle graph down below. We see our velocity time, and we see the positive slope, which we know means increasing velocity as time goes on. If we look at the acceleration time graph in the bottom right, we see that that's happening also. There's a straight line there, so there is constant acceleration, which we also know from the velocity time graph because it is a straight line, okay? The position time graph shows us the same thing. We are moving in a positive direction because we are adding to our position as it goes here, and we are doing it more quickly as time goes on, thus the curved line. The curved line being curved in itself implies not only that it is moving because the position is changing with some velocity, because it has to be in order to be moving, but also that is accelerating because it begins to change at a different rate. So all three of these graphs at the bottom would describe an object moving in the positive direction that is increasing its velocity. And I can get that just because I understand what's on the axis of each graph and what those curves mean within that, okay? So I think this is great because this expands upon what you just looked at. It does it in the negative direction. So you see the curves happening in the negative direction down below this, this GIF here that's being shown at the top. And it shows the graphs being made as it goes there. So the dot is actually meant to signify per same amounts of time how something is spreading apart. And we have an example of this we'll do in class as well. But each dot note is further apart. Okay, that implies an acceleration. This happens to be a negative acceleration because it is increasing velocity in the negative direction. So we see our position time graph with the curve. The curve again signifies some acceleration being present. We can see that on the acceleration time graph in the bottom right. And we see that we have a constant form of acceleration, not just because the line is flat in the acceleration time graph, but also because it has a constant slope on the velocity time graph. All right, so that's our basics for graphs. I want to see what we can do here. So I want you to look at A, B, C, and D. A in the top left, B in the bottom left, C in the top right, and D in the bottom right. To look at what's on those axes. Remember, I know the axes are slightly cut off for the bottom ones, but that will always be time. Look at the y-axis, pause this briefly, and figure out which ones of these have a constant velocity. All right, now that you are back, A, we have a position time graph. It has a constant slope, so there is a changing position. So we are going to have a positive constant velocity for A. So A, yes, positive constant velocity. B, if we look at that one, we have a flat line on a position time graph. So here we would have no velocity. Now, I asked if it was constant velocity. it is constantly zero velocity here. So I would say for this one, yes, it has a constant velocity of 0. All right. Looking at C, I have a moving line, or a sloped line on a velocity time graph. The slope on the velocity time graph implies that the velocity is different values as time goes on. And so, no, it is not a constant velocity. It is a changing velocity, and thus there is some acceleration. And it's going to be a negative acceleration because we have a negative slope. And if we look at D, we have a straight line on a velocity time graph, which implies the value of velocity is the same the whole way through. So we would have a constant velocity here. All right, now these very simple equations that we saw to start off here, right? Velocity is delta x over t, right? Change of position over time. And acceleration is delta v over t, so change in velocity over time. Those can be rearranged to make what we refer to as the kinematic equations. The easiest one to see that rearranging with is that top one. If I take that v naught, that initial velocity is v0, all right, the starting velocity, and move it to the other side, I get my delta v. If I divide that at term by t, then I get a equals delta v over t. And that's our basic equation for acceleration. It's just been rearranged. These kinematic equations are equations where we have substituted in the different equations together to make things more usable for you as you solve some of these problems coming up. So I want you to be familiar with these. They are on your equation sheets, and we will talk much more about these in class also and how to use them. But these are rewritten versions of your velocity and acceleration equation that make them much more usable in the terms of solving specific real-world problems. All right, we have 2 practice problems here, 1 and 2. We will spend a little bit of class time solving these practice problems, so we will visit those during class hours. The next thing I need to get into here is gravity. All right, and now before we think, okay, wait, we're talking about kinematics, gravity is a force, and that's supposed to be in the next unit. You are correct, but gravity does cause objects to begin moving, right? If you hold out an object and release it, it is going to increase in velocity. It's going to accelerate as it falls. And so gravity drives a change in motion more so than anything else on this planet. And so I want to make sure that we talk about that. So it's a natural phenomenon by which all physical bodies attract each other. It gives weight to objects with mass, and while all objects with mass will have some gravitational pull on other objects with mass, the greater the mass, the greater the pull of gravity that is generated. And this is why, even though all of us everywhere and all the things around you, not all the things, but the substantial things around you have mass, you're not attracted to each other. And your computer isn't flying into your face right now as you watch this because there's an object close to you that has a significantly and a number of orders of magnitude greater mass, and that's the Earth. So it pulls all things towards it because the gravitational pull of the Earth on you is much greater than you and the computer that you're looking at this with to each other. All right. I include this image because I really like it because it brings back to Isaac Newton the first time he kind of defined this. It was defined by the church at the time as the statements of a lunatic, and that the apple must have hit him in the head. And that's the common story about how Isaac Newton discovered gravity as if it wasn't there beforehand. But what actually happened was he observed apples falling downwards. He wondered why they always fell in the same direction, and thus hypothesized that they moved towards the largest object, and that eventually led to the theory of gravity. All right, I love Calvin and Hobbes. So my son's middle name is Hobbes. I wanted to throw in a quick Calvin and Hobbes here. I thought this was great. Calvin, unfortunately, he says he couldn't read his homework because his parents forgot to pay the gravity bill. All right, objects in free fall. So to go to how gravity directly affects things, an object that is only being acted upon by gravity is said to be in free fall. This is something that if you were to just hold an object and release it, or to let something fall off a cliff, or to have people who want to skydive jump out of a plane, that is how these are being affected and how their velocity increases. causes objects that have relatively small amounts of mass to increase velocity as gravity attracts them to objects of relatively large amounts of mass. The relative piece of that is very important because it's going to be a little bit different when we look at objects of relatively similar size masses, like let's say the Earth and the Moon. But we'll get to something like that in our next unit. Velocities for objects in free fall are going to increase. Okay, free-falling objects will increase in velocity, and this is specific to Earth because it's based on the pull of the Earth, but they're going to increase in velocity by 9.8 meters per second for every second that they fall. So meters per second. So they are accelerating. Again, if you drop an object, it doesn't stay stationary. Its velocity increases, and the longer the amount of time that it has to fall, the faster that it will go. Okay? This means that an equation can be derived to determine this. And before you write this down, this is not an extra equation. I'm going to talk about that g in just a second. It's really just a form of acceleration. But we could say that the final velocity of an object in free fall, so with no other forces acting on it, would be gt. G being our gravitational acceleration, or also said, acceleration due to gravity. Objects here on Earth, based on the size of the Earth, accelerate at 9.8 meters per second squared. And you see the picture over on the right that helps signify that a little more appropriately. The ball is spaced apart as time goes by, similar to the other objects accelerating that we looked at earlier. And you see from 0 to 1 to 2, 3, 4, 5 seconds. In each case, it is increasing in velocity by 9.8 meters per second. So the amount of time that it's been falling in seconds times 9.8 meters per second squared will give its velocity in meters per second. All right, so in order to use this, we must assume that the object is being dropped from rest. If this kid throws the ball downwards, then it's going to have different velocities there. So if you give it an initial velocity, a starting velocity, this will be a little different, but an object in free fall, thus dropped, beginning with no velocity, will increase just like this. Right? A similar correlation can be made with the distance that an object falls. Okay, so if it is moving with the same velocity change as it goes there, we can also describe the distance that it travels in a similar way. So the distance that it's traveled there, or we could even say delta x, how far it has moved from its starting location, will be 0.5 or 1/2 gt squared. All right, our gravitational constant, 9.8 meters per second squared, times our time in seconds squared. That will get rid of our seconds and leave us just with how far it's gone, the distance that it's traveled. And you see that there on the left also. And those are going to increase at a much greater magnitude as they move along there. Okay, we got to make those same assumptions. Now I'm going to look real quick. Distance, also known as x here, 0.5 gt squared. 1/2, and remember g is an acceleration, at squared. Here we have a velocity equals gt. Remember g is an acceleration, at. If we go back and look real quick at our kinematic equations, okay? The first one that you were looking at there is that top equation. Velocity equals, well, the starting velocity was 0, so that v naught is 0. We got rid of that. At, well, a is g in the case that we're looking at there. So velocity equals acceleration times time. The second one that you saw there, that distance equals gt squared. Well, if we look at the bottom one, that delta x, or the distance traveled, well, again, the v naught, the starting velocity was 0. So that first term, v naught t, that v0t, that can be canceled out. 0 equals 0.5 gt squared. Well, 0.5 and 1/2 are the same thing, and g is a form of acceleration, so we've got that bottom equation there. So we basically just proved the first and the third kinematic equations just by looking at how objects move through free fall. Okay? We need to make a note on this. And normally in person, I would have stated this numerous times. But whenever we do this, we are going to neglect air resistance. I 100% realize that if you drop different objects, one with much more air resistance than the other, that they will not fall at the same constant velocities because there is air to block them. Okay, by that I mean, if I dropped a bowling ball and a piece of paper at the same time, they're not going to fall with the same velocity, right? Because the piece of paper will have much more air resistance than the bowling ball. In class, I will show you a video that proves that without air resistance, they will fall with the same velocity, but we will get to that in class. for our calculations, we must neglect air resistance because we're just not at a point yet where we can do that. All right, so we've got a sample calculation here. Again, we'll work through some of these as we go through. Well, this one's got the solution in it, so let's talk about this real quick. An object is dropped into the Grand Canyon. It falls for 6.3 seconds before hitting the ground below. How fast is the object going when it hits the ground, and how far below it was dropped does it hit the ground? So just using those equations, V is gt, that 9.8 meters per second squared, times the 6.3 seconds it fell. You can see how fast it was going at the bottom. And then 0.5 gt squared, we're plugging our numbers in there as well. And we're seeing in both cases, well, I'm sorry, in the second case, that those seconds are canceling out. Meters per second squared times seconds squared, that leaves us with just the meters. All right, the last thing we need to get into, the big end piece for this unit, is projectiles and objects moving in two directions at once. So a projectile is any object fired into the air. An example could be a golf ball off a tee, a thrown football, anything that moves to some degree through the air. It has a path called a trajectory, and you could absolutely describe the path that it would take, and hopefully the diagram below helps describe that to some degree also. It's often referred to as projectile motion, with the object moving through the air being that projectile. So you might see that listed, or you might see motion in 2D. The big difference there is motion in 2 dimensions could just refer to an object moving along the ground if you're looking at both an X and Y coordinate plane, whereas projectiles typically refers to objects moving through the air because then gravity affects them, whereas objects rolling along the ground that might be moving in both directions through an XY coordinate plane, gravity is not necessarily affecting that. It is for projectiles. So speaking of those things affecting projectiles, there are 2 forces that will affect them. Gravity being one, that's pulling it back down. This quarterback doesn't throw the football and have it keep moving all the way out into space. It does come back down eventually. Okay, so it will bring things back down at a constant acceleration, which we just talked about with free fall. The other thing is air resistance, and you'll hear me use this term negligible in a lot of different times, all right? That means that it's going to be so small that we ignore it, or that the calculation would be so complex that we're just not going to do it at this point early on in your physics education. So air resistance is going to be negligible. We're going to ignore air resistance. The path all projectiles take is parabolic. It's going to be parabolic in shape because of the forces acting on them. So here, now there is one angle where it won't be, but I'll talk about that in just a sec. But here we see an object launched at numerous different angles, and we will do some sims. Normally in class, full class, we would do some labs that will show that this is the case. And if you think about any object moving through the air, this is probably what you picture as it moves. So you see the launch angle of different objects and how they will move and travel different distances based on the angles that they are launched. We'll move much deeper into that as we get into the rest of this unit. The one angle that this parabolic shape is not the case is if an object is fired straight up. But let's be honest, only fools are firing objects straight up because they're going to come straight back down. So 90 degrees is the one spot where you won't have this shape. It will just move straight up and then straight back down. I want to talk real quick about a world without gravity. So let's imagine for a second there is no gravity. The direction of all projectiles is never going to change. It's going to move on continuously, okay? So they continue along their initial path forever. So let's say you just jump up while you're outside. No gravity means see ya, because you're just going to float on forever. Because gravity's there, we come back down, we land back on the earth. So some smart guy once stated this as a law. His name's Ike. Actually, his name was Isaac. We've mentioned him already briefly, but Newton's first law here. It's an object at rest will stay at rest unless acted upon by an outside force, and an object in motion will stay in motion unless acted upon by an outside force. And you've probably heard this in some sort of vocabulary before, but it is very, very important. Okay, now we do have a constant force acting on things here on Earth, and that is the force of gravity. So we can keep that in mind. All right, in our 2 directions, you're going to see right now, and you probably see in this diagram, why I spend an intro unit talking about vectors. Okay, vectors help us describe motion as it moves through these 2 different dimensions. So although projectiles move in 2 directions, gravity only pulls them downwards. Okay, so I want to think about this real quick. We have a gun that can fire a bullet and a person that can throw a ball. Both will be pulled down if fired horizontally, perfectly flat. Both will be pulled down to eventually hit the earth. One will travel a much greater horizontal distance before doing so. That's because it's fired with a much greater Vx, as you see in this diagram, a much greater horizontal velocity. A gun fires a bullet much faster than a person can throw it. Okay? They will both eventually fall to and hit the earth, no matter what, because gravity pulls on them. So we have to break our projectile motion into components in order to properly understand how this works. You see some important things happening right here. Number one, an object is thrown off the edge of a cliff. It begins with some resultant velocity, and you see that Vx naught, so the initial velocity in the x direction is right there to the arrow pointing to the right at the edge of the cliff, and Vy naught, I know that sounds odd to say why not, but the initial velocity in the y direction there as well, okay? Notice that the y velocity gets smaller until we get to that point known as the apogee, and then increases as it falls downwards. That's because as it goes up, the acceleration due to gravity slows it down to be 0 at that apogee point, and I'll further define that in just a moment, and then increases the velocity in the y direction as it falls downwards until it hits an object. Okay? Now the apogee is that instant in time, and it's not actually any amount of calculatable time, but it's that very, 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 very brief moment where it stops moving up and begins moving down. That is an important point that we will talk about more in the future as we go through these types of problems. But the apogee is the height of motion of a projectile object. Now, I want you to notice something else on this. The Vx vector has the same magnitude throughout. That happens because there is no standard acceleration in the x direction. Gravity only moves things up and down. I'm sitting here. You've seen me in this image in the bottom right. I haven't moved side to side because gravity is not affecting me that way. Okay? It is pulling me down into my chair, and that's why I'm staying right here. All right? The velocity in the x direction does not change. It is constant because there is no acceleration to change it. And in order for it to change, we would have to have an acceleration by the definition of both terms. Right? The velocity in the y direction is changing because we do have an acceleration in that direction, and that acceleration is gravity. So to look at this again, and now we actually have gravity denoted at the top of this graph, moving downwards and thus affecting the velocity. Now I like to look at this graph second, or this image, I guess, second, because it shows the resultant velocity of both as you're moving through this motion. Okay, so in the bottom left corner at our origin coordinate spot on the xy axis, we see that Vx naught, just like we saw here, and the Vy naught, just like we saw here, but it also shows that initial launch velocity. Now, one of the reasons, again, that we looked at vectors is because you could find the component velocities, the Vx and the Vy, of that launch velocity, V, if you know the angle that it's launched at. And that's going to be a more likely given. If I give you a problem, or let's say you need to solve for how far something's going, how high it's going, that type of stuff, you're probably not going to be given the component velocities early on for these types of problems. You're going to have to find them and be able to use your trig to do that, which is why, again, we've visited vectors already. Now you see how as motion continues here from that first step in the bottom left to the next one on its way up, how that Vy has gone down. And you see how that has affected the overall vector of V as well, even though Vx is the same. All right, look at all those steps. Vx is the same length, same direction all the way through, even at the height, that apogee, that highest point, it's still the same there. But the Vy changes. It goes from a higher magnitude when it starts to less of a magnitude, still in the positive direction, to no magnitude, so there isn't any velocity in the y direction, to a negative magnitude that's in the middle in that fourth spot, to its greatest magnitude in the negative direction again at the far bottom spot on the right. Okay, this is all because, as you see, that gravitational vector points downwards the whole time and thus affects the vertical velocity the whole time. The horizontal velocity is constant, even though the overall velocity and the vertical velocity are both changing as time goes on. That is the key to all of this. So breaking this into vectors is the key. All right, these components of motion, vectors that are perpendicular to each other act independently. And we didn't cover that to a large degree as we went through our vectors, but we did talk about breaking them down into components, and that's what was implied by doing that. This means that horizontal and vertical components do not affect each other. Okay? This leads to a few assumptions when breaking motion into components. Acceleration in the y direction is 9.8 meters per second squared. As we've stated, it's gravity. Acceleration due to gravity. Acceleration in the x direction is 0, and our air resistance is negligible. Now, the key to all of this, if we were to solve some sort of problem where it's asking you how far something's going, how high it's going, how long it spins in the air, what its velocities are, anything like that for these projectile motion problems, is going to be to break the problems into two parts, the x and the y components. Now, there is a constant, and this is the key to solving these problems. Despite the fact that they are analyzed separately, there's a variable that's constant between both. If we look at this terrible pitch that's at the bottom of the screen here, and we look at how fast it's moving in the horizontal direction and how fast it's moving in the vertical direction, one thing is constant, and that is the amount of time that goes by as it moves. So from release to landing on the ground, the same amount of time is passing whether I look in the vertical or the horizontal direction. The projectile shown below will spend that same amount of time in the air, whether analyzing the horizontal or the vertical components of its motion. That's very, very important because, as you've probably guessed by now, vertical components are going to be more difficult to calculate because there's much more factors happening here. There's an acceleration in that direction that there's not in the horizontal direction. But if we figure out how long it spins in the air looking at its horizontal components, we can use that same amount of time when we look at its vertical components. That is the only constant between these two and the only thing that we can bring back and forth between them. So it's really the key to doing all of this. All right, so I'm going to exit the full screen here just because I want to play this. Of course, it's not going to play, but this is supposed to show an object moving here, and we'll play this in class then as time goes by and show the difference in the velocity in the x direction and the y direction as time goes by. We will show that then in class. I also have then two example problems for this type of motion that we will cover in class as well, but we'll go through both of these. And I just want to then revisit our very last slide, our kinematic big ideas. Big idea 3, interactions of an object with another object can be described by forces. These things don't start moving like that cannon firing an object without some interaction between two different things. And then interactions between systems can result in changes in those systems. Again, that interaction happening is what causes the velocity to occur and for the object to begin moving. So I hope you saw those in some spots. I hope this was a helpful way to look at these notes. We'll further expand in class. Have a good one.